Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module we are discussing atomic and ionic radius. Here the contents are size of atoms and ions, covalent radius, crystal radius or metallic radius, van der Waals radius, ionic radius, that means cationic and anionic radius, periodic trends, variation of ionic radii in isoelectronic species, and problems based on the concepts. First of all, size of atoms and ions. In the case of an element, its size or an ion developed from that element having certain size. The size of atom and ion is very important as far as their position in the periodic table is concerned. That means atomic size and ionic size are important periodic properties. They have some periodic trends. We are now entering into more details of atomic and ionic size. That means size of atoms and ions. The size of atoms and ions commonly referred to as atomic radius and ionic radius. That means size of an atom is interpreted in terms of atomic radius, whereas size of ion is represented as ionic radius. And this depends on various factors such as number of electrons, the effective nuclear charge, and electronic configuration. So, size of atom governed by atomic radius, size of ion governed by ionic radius have some close connection with the parameters like number of electrons, effective nuclear charge, and electronic arrangement or electronic configuration. Now, the ionic radius is the measure of the distance from the nucleus of an ion to the outermost electron in its electron cloud. Let us consider the case of Cl minus ion. You know it is an anion. It is obtained by the addition of an electron to the chlorine atom. Then there is a distance from the center of the nucleus of the Cl minus to the outermost electron or outermost electron cloud. That distance is taken as the ionic radius. If it is the case of a cation, you can call it as cationic radius. Similarly, if it is an anion, if you are dealing with an anion, you can call the radius as anionic radius. It represents, the ionic radius represents the effective size of an ion when it is part of crystal lattice or in a chemical environment. This is the definition part of ionic radius. Now, the distance from the nucleus of an atom to the outermost electron shell in an atom is taken as atomic radius. So, atomic radius is the distance from the center of the nucleus of an atom to the last electron. The probability of finding an electron is never zero even at large distance or infinite distance from the nucleus. That means, according to the principle of the quantum mechanics, we can say that even at infinite distance from the nucleus, the probability, the possibility of finding an electron is not equal to zero. That's why it is very difficult to represent, to find out exact value of atomic radius or even ionic radius. Based on the probability concept, an atom does not have well-defined boundary. Once if it is there is a clear-cut boundary, you can measure the distance from the center of the nucleus to that boundary position. In the case of atoms and ions, based on the probability concept, there is no clear-cut boundary. So, the demarcation of the distance from the center to the boundary is not a clear concept, or it is too tough or difficult to find out the exact value of atomic and ionic radius. Or we can conclude like this: the exact value of atomic radius or even ionic radius cannot be evaluated. In order to address the difficulty in evaluating the perfect value of atomic and ionic radius, we simply represent atomic radius in into 3 different types. This is for the sake of convenience and for the sake of determination of the values of atomic radius. That is, atomic radius can be mainly 3 types. These 3 types are shown here. It may be covalent radius, metallic radius and van der Waals radius. We can now move on to details of each of these type of atomic radius. The first category, that is nothing but covalent radius. Covalent radius is defined as 1/2 of the distance between, it is 1/2 of the distance between the nuclei of 2 covalently bonded atoms. That means if 2 atoms are connected via covalent bond, then the distance between the 1/2 of the distance between the centers of the nuclei is taken as the covalent radius. This is the pictorial representation. This is first atom A, this is second atom B. Both are same element. So, these elements are XX and the distance from the center position A to B, take its 1/2 and 1/2 is R covalent or covalent radius. That is, R covalent is equal to half of the distance AB. That is, this represents, half AB represents the covalent radius of the covalently bonded molecule X2. This is generally used for studying non-metals. That means the concept of covalent radii is mainly applicable to non-metals. For homonuclear diatomic molecules, we can calculate the covalent radius by using this simple expression. DAA is equal to RA plus RA, that is equal to 2RA, and RA is equal to DAA by 2, where DAA is the distance between the centers of the nuclei of 2 atoms A. That is, A to A distance divided by 2 simply represents RA. For example, in the case of chlorine molecule, the distance between the 2 chlorine nuclei is approximately 198 picometer. So, the covalent radius of chlorine is 198 by 2, that is equal to 99. This I can represent it by a simple illustration. This is the first chlorine atom. I am again representing a second chlorine atom. These 2 chlorine atoms are held together by a covalent bond. This is the center of the nuclei of the first chlorine, and this is the center of the nuclei of the second chlorine. There is a distance, and this distance is taken as DAA. This distance is taken as DAA, and you have to take 1/2 of that distance. And in the case of the chlorine molecule, that DAA is given as 198 picometer. So, the distance from the center of first chlorine to the second chlorine is equal to DAA, that is equal to 198 picometer. If you just divide it by 2, 198 by 2, that is, the value will be 99 picometer. So, the covalent radii of the chlorine is 99 picometer. For heteronuclear diatomic molecules in which electronegativity remains approximately same, we can calculate DAB equal to RA plus RB, and there is another category for heteronuclear diatomic molecules AB, where difference between electronegativity values of A and B is relatively larger. In that circumstance, we can calculate a covalent radius by using a special expression. That is, here DAB is equal to RA plus RB minus 9.0 into delta chi, where delta chi represents electronegativity difference between the 2 atoms A and B. This formula for calculating distance between the centers of the nuclei, that is DAB, is given by Stevenson and Shoemaker, and this equation is known as Stevenson-Shoemaker formula. And DAB divided by 2 will give you the covalent radius. So, you can calculate the covalent radius for homonuclear diatomic molecules, heteronuclear diatomic molecules with negligible difference in electronegativity, heteronuclear diatomic molecules with considerable difference in electronegativity. So, for calculating the covalent radius of heteronuclear diatomic molecules with considerable difference in electronegativity, we have to use Stevenson and Shoemaker formula, which is DAB is equal to RA plus RB minus 9.1 delta chi. Remember, delta chi represents the electronegativity difference between atoms A and B of the heteronuclear diatomic molecule AB. This electronegativity values, the delta chi is the electronegativity difference, and the electronegativity values are given by the Pauling scale, and it should be noted that in this expression the radius must be in unit of picometers. 1 picometer equal to 10 raised to minus 12 meter. So, all the measurements, all the distances are in picometer, and chi must be in Pauling scale of electronegativity. We are entering into second type of atomic radius, that is nothing but the crystal radius, which is otherwise called metallic radius. It is defined as, the metallic radius or crystal radius is defined as half of internuclear distance present between the two adjacent metal ions in a metallic lattice. You are familiar with the concept of lattice in metallic crystals. Every metallic crystals are associated with some crystal lattice or metallic lattice, and this metallic radius is related to arrangement of the metal particles, metal atoms in the crystal lattice. Covalent radius is always lower than, this point is very significant, covalent radius is always lower than metallic radius, since in the case of metallic radius there is no overlapping takes place. You know the fact that whenever two chlorine atoms combine together to produce a Cl2 molecule, there occurs some overlap. As a result of that overlap, the distance between the centers of the nuclei may become more closer. However, such overlap is not possible whenever you are dealing with a metallic crystal lattice. So, metallic radius is greater than covalent radius. Otherwise, we can say covalent radius is always lower than metallic radius. This is the pictorial representation depicting the metallic radius in a crystal, in a metallic crystal. You can see the arrangement of the metallic crystal. In a metallic crystal, according to the electron C model, there are positively charged metal ions embedded in a sea of electron. That model is called Drude-Lorentz model or electron C model of the metallic crystal. This metallic bonding can explain most of the observed features of the metal ions, and the metallic radius is depicted here. In the metallic crystal, there is a sea of electron, as I just mentioned, and the positive charged metal ions are otherwise called kernels. Generally, metallic radius is present between two metal atoms, or we can simply say that metallic radius or crystal radius is exclusively for metal atoms or metal crystal. The third category of atomic radius is here, that is nothing but van der Waals radius. Van der Waals radius is defined as 1/2 the internuclear distance between nuclei of two non-bonded isolated atoms or adjacent atoms belongs to neighboring molecules. This is the pictorial illustration of the van der Waals radius. You can see the presence of two diatomic molecules. These two diatomic molecules are nearly very close to each other. See this distance, this solid line represents the distance between two non-bonded atoms belongs to neighboring molecules. This atom is from first molecule, this is from the second molecule. So, there is a distance, this distance is non-bonding distance. That non-bonding distance, 1/2 of that non-bonding distance is considered as the van der Waals radius. It is also defined with respect to inert gases. It should be noted that in the case of the inert gas, there is no bonding. Even there is no diatomic noble gas is present. Helium cannot be bonded to another helium. They are individual atoms. They are always having stable electronic configuration and they will not combine mutually. So, in such a case, you can also define van der Waals radius like this. In such a situation, in the case of the noble gas, this van der Waals radius is defined as 1/2 of the internuclear distance present between atoms of inert gas in the solid state. So, in the case of inert gas, we are considering the distance between atoms. They are already non-bonded, but you have to consider this noble gas that must be in the solid state. Van der Waals radius does not apply to metal, and its magnitude depends upon packing of atoms when the elements are present in the solid state. As far as the close packing is concerned, if the packing is very closest, then it definitely affects the van der Waals radius, since it is the distance between the non-bonding atoms. Now we can have a comparison of covalent radius, van der Waals radius together. That is, we are comparing how covalent radius and van der Waals radius are connected, how their magnitude differ each other. This is the pictorial representation. The first molecule is a diatomic molecule. The second one is another diatomic molecule. The distance between the centers of the nuclei is one half the distance between the centers of the nuclei is termed as this distance, and one half of that distance is taken as the covalent radius. And you can see the presence of the van der Waals radius also, and van der Waals radius is comparatively very high when compared with the covalent radius. The van der Waals force of attraction are always weak. Therefore, internuclear distance in the case of atoms held by van der Waals force are much larger than those between covalently bonded atoms. You have to keep this point in your mind. In the case of van der Waals radius, there is no bonding interaction. However, in the case of covalent radius, there is overlapping and bonding interaction. Bonding interaction causes decrease in bond length, and hence covalent radius are always less than van der Waals radius. Now, a covalent bond is formed by the overlapping of two half-filled atomic orbital, and in this part of the orbital becomes common. Therefore, covalent radii, as I mentioned, are always smaller than the van der Waals radius. This is a representation of elements and their covalent as well as van der Waals radius. Consider the case of hydrogen. The covalent radius is 0.37 angstrom, whereas the van der Waals radius is very high, that is equal to 1.20. Similarly, in all the case of elements, in all these elements, hydrogen, oxygen, fluorine, sulfur and bromine, you can see that the third row, that is van der Waals radius, is higher than the second row, that is nothing but the covalent radius. So, in general, if you are considering all the three kind of radii, that is van der Waals, metallic and covalent radii, the biggest value is associated with the van der Waals radius. After that, metallic radius, and the least value is associated with the covalent radius. Now we are considering another aspect, that is size of ion governed by ionic radius. We are now entering into the details of ionic radius. The ionic radius refers to the size of an ion and varies depending on whether the ion is a cation or anion. You are familiar with the two kind of ions, the positively charged cation and the negatively charged anion. Cations are produced by the removal of an electron from a neutral atom, so it is associated with a high nuclear charge, and an anion is formed by the addition of an electron towards a neutral atom. So, electronic charge is high compared with the nuclear charge. So, there are two kind of ions. Na plus is an example for a cation and Cl minus is a nice example for an anion. And we are discussing the cationic as well as anionic radius. Cations are positively charged, formed when electrons are loosed by an atom. Similarly, it should be noted that anions are formed by the addition of an electron to an atom. And this point is very noteworthy. Cations are smaller than parent atoms. It is very significant thing. For instance, I can say that sodium atom is bigger than Na plus, or simply Na plus cation is smaller than sodium atom. Or in general, you can say that cations are smaller than their parent atoms. Calcium 2 plus is smaller in size when compared with the calcium. Aluminium 3 plus is very small when compared with the aluminium atom. Every cations are smaller than their parent atoms. This is exemplified by taking the exact numerical value of radius of sodium atom, which is equal to 186 picometer. When sodium atom loses one electron and it is converted to Na plus ion, its radius, its cationic radius, decreased to 102 picometer. See the difference. Sodium atom is having atomic radius 186 picometer. Na plus cation is having very small size with 102 picometer as cationic radius. Anions are ions with a negative charge formed when an atom gains one or more electrons. It should be noted that anions are larger than their parent atoms. A very nice example is here. Cl minus is bigger in size when compared with the chlorine atom. Chlorine atom is the parent, Cl minus is the anion. When Cl is converted to Cl minus, there is an increasing radius which is exemplified by chlorine atom is having a radius, covalent radius of 99 picometer. When Cl is converted to Cl minus by the addition of one electron, the ionic radius, the anionic radius will be 181 picometer. See, there is a drastic increase in the ionic radius. So, when an atom is converted to an anion, a negatively charged ion, the size will be increased. In general, you can conclude that anions are larger than their parent atoms. O2 minus is greater than oxygen atom. N3 minus nitride ion is bigger in size when compared with the nitrogen atom. Every anions are larger than their parent atoms. Now the question arises, why cations are smaller than parent atoms? This you have to keep in your mind. This happens. The cations are having small size than their parent atom happens because of the following features. Loss of electron reduce electron-electron repulsion, allowing remaining electrons to be pulled more closer to the nucleus. The nuclear charge remains unchanged. So, the nucleus pull the reduced number of electrons more strongly towards itself, and hence size of the cation is decreased when compared with an atom. And another question is just opposite to the previous one. Why anions are larger than the parent atoms? The answer is here. This happens because addition of electron increases electron-electron repulsion because there is an increase in number of electron which cause the electron cloud to expand. That means electrons will move away from the nucleus, which leads to increase in size. The nuclear charge remains constant, but it must spread over more electrons, reducing its ability to pull them more tightly. That is, electrons will move away from the nucleus, leading to bulging in the structure, or size of anions are always greater than the corresponding. Discussing factors affecting atomic and ionic size. These are some factors. First one, nuclear charge. A higher nuclear charge leads to small size. That is, as the nuclear charge increases, it pulls electrons more close together, and there is a decrease in size is observed. The second feature is electron shielding. Inner electrons shielded outer electrons from the nucleus, which leads to increase in size. Number of electron shells. More number of shells, the size will be higher. That is, size proportional to number of shells. Electron-electron repulsion is another parameter that affect atomic and ionic radius. More electrons are present in the same shell, there is an increased repulsion between electrons, that is, interelectronic repulsion is high, and hence the size is also high. Now we are discussing periodic trends in atomic radius. First of all, we are discussing the periodic trend along a period. As we move from left to right, we are checking what happened to the atomic radius. This is the result. Atomic radius decrease as you move across a period in the periodic table. If you move from left to right across a period in the periodic table, you can see that there is a decrease in atomic radius. The reason is here, atomic radius inversely proportional to effective nuclear charge. As the effective nuclear charge increases, atomic size decreases, and vice versa. This is due to the fact that an increase in nuclear charge, more number of protons in the nucleus means increase in nuclear charge, which pulls electrons close to the nucleus without significant addition to shielding. So, with the high nuclear charge, size decreases considerably. This is illustrated here. Sodium, magnesium aluminum, silicon, phosphorus, sulfur and chlorine. All these elements belongs to same period in the periodic table. This is an illustration of their size. You can say that sodium is bigger in size, at the same time chlorine is smaller in size. So as we move from left to right, there you can see a decrease in size. Now, the periodic trend in atomic size down a group. Down a group means as we move from top to bottom in a group. Let us check what happened to atomic radius. Atomic radius increases as you move down a group. As we move from top to bottom in a group, you can see that there is an increase in size. This happens because electrons are added to higher energy levels or new shells. So as you move from lithium to sodium, you can see the presence of a new shell. From sodium to potassium, there is one more shell is added. So electrons are added to the extra shell, which are the new shell or extra shell are farther from the nucleus. Atomic radius directly proportional to number of shells. With increase in number of shells, there is an increase in atomic radius. Increase in shielding by inner electrons reduce the effect of the nuclear pull to the outer electrons. There is a shielding effect. Shielding effect means the intervening shells containing electrons prevent the attraction of the nucleus from the outermost electron. So you can see that with increased shielding, there is an increased size, increased atomic radius. This is clearly depicted in this picture. Hydrogen is having smaller size than lithium. Sodium is having bigger size than lithium. Potassium is again having bigger size than sodium, and rubidium is having highest size among these elements. So as we move from top to bottom in a group, number of shells are increasing, and hence you can say that size of an atom governed by atomic radius increases from top to bottom in a group. Now, a very significant question: why inert gas has maximum size? The answer is here itself. In the case of inert gases, we consider van der Waals radius, and van der Waals radius is greater than that of metallic and covalent radius. See, if you are considering the case of the helium atom, in the case of helium cannot bond to any other helium atom because it is an inert gas or a noble gas with a stable electronic configuration. So helium atom is an individual atom. So you cannot calculate the covalent or metallic radius of helium atom. There is one and only radius, that is nothing but the van der Waals radius. We previously discussed that the magnitude of the van der Waals radius is very high compared with the covalent as well as metallic radius. So the answer is here, inert gas have maximum size because the radius mentioned for noble gas is van der Waals radius, which is greater than the covalent as well as metallic radius. This is a trend in the atomic radius. In this series, in the first series, you can say that the biggest size is associated with the neon, and in the second series there is a gradual trend. However, that argon element, the element argon is associated with a very high radius, and in the case of neon and argon, both are noble gases. The radius mentioned is nothing but the van der Waals radius. Variation of ionic radii in isoelectronic species. What is meant by isoelectronic species? Isoelectronic species are species having same number of electrons. For ions with the same number of electrons, ionic size decreases as nuclear charge increases because atomic radius is inversely proportional to nuclear charge. Now consider some species, isoelectronic species. Oxygen 2 minus 8 plus 2, oxygen having atomic number 8 plus 2 electrons, so it is a total 10. F minus is also having 10 electron. Sodium plus is having 10 electron. So all these species are having 10 electron. All you can consider as isoelectronic species, and the size is least for aluminum 3 plus because it is a positively charged species associated with a high nuclear charge. As the nuclear charge increases, there is a decrease in size. Now, variation of ionic radii in ionic species, in isoelectronic species, another illustration. Consider nitrogen 3 minus, oxygen 2 minus and F minus, nitride oxide and fluoride ion. you can see F minus is associated with the small size. The reason is simple. In the case of N3 minus, the nuclear charge is very low compared with others. Higher the nuclear charge, smaller will be the size. So, in the case of F minus, the size is very small. That is N3 minus greater than O 2 minus greater than F minus, even though all have the same number of electrons, size follows this range. Consider some cations, Li plus, beryllium 2 plus, boron 3 plus and carbon 4 plus. It can be concluded that all these species having 2 electrons and highest size is associated with Li plus. The least size of carbon 4 plus is due to its very high nuclear charge. So, ionic radius is inversely proportional to nuclear charge. Now, some problems based on the concept we have discussed so far. This is an MCQ. Why the ionic radius of Cl minus is larger than Na plus? This is the question. And these are the options. Cl minus has a high nuclear charge than Na plus. Cl minus has more electrons than Na plus, leading to greater electron repulsion. Na plus has more protons than Cl minus. Ionic radius does not depend on charge or electrons. Based on careful analysis, we can arrive at the final answer as answer option B. Cl minus has more electrons than Na plus, leading to greater electron-electron repulsion. And this is another MCQ. In the isoelectron species O2 minus, F minus, neon, Na plus and Mg2 plus, which ion has the smallest ionic radius? These are the options in front of you. This is a direct question. You can arrive at the answer that option D is your answer, magnesium 2 plus, which is associated with high nuclear charge. Higher the nuclear charge, smaller will be the size. So, Mg2 plus is associated with the very small ionic radius. This is another one. Arrange the following ions in the increasing order of size. Again, some isoelectron species O2 minus, F minus, Na plus and Mg2 plus. And these are the options. On careful analysis, it is very well clear that your answer is option B. Magnesium 2 plus is least in size and oxygen 2 minus is bigger sized anion. Which of the following is an example of an isoelectronic species? On careful analysis, we can arrive at the final answer as option B, O2 minus, F minus, neon and Na plus, all having 10 electron and belongs to isoelectronic species. This is a match the following type of question. Match the terms in column A with their corresponding numerical values in column B. Column A represents atomic radius of K, K plus aluminum and aluminum 3 plus. Column B represents some numerical values, and you have to compare based on the logic you have learned. Cations having smaller size than the corresponding atom. Anions having smaller size, bigger size compared to size of atom. Higher the nuclear charge, size will be small. Based on these arguments, we can arrive at the final answer as for potassium, the atomic radius is 243 picometer. For potassium plus, the ionic radius is 138 picometer, and atomic radius of aluminum, that is equal to 143 picometer, and ionic radius of aluminum 3 plus is the least, and that is nothing but 53 picometer. So, your option is 1C, 2A, 3D and 4B. This is another match the following type of problem. In the column A, there are some ionic radius and atomic radius. In the column B, there are corresponding numerical values. So, based on careful analysis and by applying the principle that atomic and ionic radius inversely proportional to effective nuclear charge, you can find out the answer as 1B, that is atomic radius of lithium equal to 152 picometer. 2A, that is ionic radius of Li plus equal to 76 picometer. 3D, that is atomic radius of chlorine is equal to 99 picometer, and 4C, that is ionic radius of Cl minus is equal to 181 picometer. That all about the discussion on the present module. Have a nice learning experience. Thank you.